really excited to be included in the program. This is an issue that I've been working on for at least a decade, and it's something that I think is very important in the context of the changes that we are seeing as the electric power system becomes more digital and we have more distributed resources, particularly within the distribution network. Part of my role today is to lay out some foundational concepts that the later speakers will then be able to build on. And so I want to start with some definitions, and then hopefully later when we get to other speakers, you'll be like, oh, that's why she mentioned that. So I'm going to start with some pretty basic things. First of all, what do we mean by a system? You know, we think about the electric power network as a system, a distribution system. And we see this also throughout all sorts of other parts of our economy, and especially when we think about digital systems, that we see a system as a configuration of parts connected by a web of relationships. So we can think of the internet as an example of a configuration of parts, including all of our own devices, connected by a web of relationships. And the relationships determine how those parts interact with each other. And if one of them is generating data and sending it to another one of them, the relationship tells you what direction that data is going to go, how to understand and interpret the data, and what, if anything, to do in response to the data. And so that's a very general idea of a system. But systems are not just digital. We can think of the system, and I've put up here the kind of, I think, standard schematic of the traditional electric power system and the one-way road from large-scale central generation through to the end user. And that is itself a sort of system. What we're talking about today is the idea of a distributed distribution system that has more heterogeneity, more distributed resources at different scales and in different locations. And how do we make the best use of those and actually turn them truly into system resources, in addition to the individual benefits that those resources, such as electric vehicles or rooftop solar, provide for the owners. Another important concept to define is the idea of a system being modular. Modular means that you have components that are standalone and can be separated and recombined. So in terms of a computer system, for example, you can think of your laptop as a modular component in a broader computer system. You can pick it up, you can go to some other piece of the internet, some other wireless network, log on, and you still get to go do your thing with your laptop. If you buy a new laptop and get rid of your old laptop, it's, you swap the one out and swap the other one back in. And so that's an example of modularity. And modularity and the kind of plug and play idea is also something we see in this technology that we all use in many different ways in our lives, right? The USB interface. That brings us to the idea of architecture. And architecture is basically how we design this system. And the design of a system is really designing the relationships among the components, and that there is some objective there. When we design a system, as opposed to systems that emerge or are self-organized, when we design a system, we have some objective. And that objective, I'm going to generally say, is that there is some order in the system. In an electric power network, that order can be maintaining physical balance in the system. I've put a caveat on here that says don't fall into the optimality trap. One thing that we do a lot as engineers and economists, I think, is we model out and we simulate what's the optimal architecture and the optimal system. Every computer scientist and engineer that I've ever talked to about implementing systems in the real world, from electricity to financial services, has said, you design the optimal and that's not how it turns out in reality. So don't let the perfect be the enemy of the good when you're thinking about this. And then finally, one of the most important fundamental principles, I think, for our application in energy is the idea of interconnection, that in systems you connect components to each other in a system. And one of the real reasons why we are thinking about these issues of interoperability today is the technological dynamism and the innovation that is bringing more distributed resources into the system. And we are exploring how it is we can facilitate their interconnection and turning them into true system resources. And so that is why we are going to be interested in interoperability, because we are increasingly having a digital electric system with distributed resources, and we are going to have components that we want to work and play well together with each other and generate value for individuals and for the system as a whole. And that's why interoperability is important, because interoperability is the principle of making sure those devices work well together. For our purposes as policymakers and policy analysts, we're interested in why we should care about this. You know, is this just a technical thing? I think Tricia's comments are very apt that there's technical interoperability, but that interoperability is a multi-layered thing. And so I'm going to lay some foundational claims out that we will develop over the course of the rest of the workshop. And I want to start with the kind of basic policy objectives that we know that we've had for decades: safety, reliability, and affordability. And that interoperability is a very useful concept that we should focus on in advancing those policy objectives. So for example, safety, we can think about the response to significant events such as weather events. You know, a big thunderstorm comes through, having neighboring utilities being able to help each other out because their systems are similar, right? They have a common shared understanding of what these, how these systems operate. And that's, you know, very important. For interoperability, for reliability purposes, means that we can use digital technologies and the interconnection of them in the system to get better monitoring, better communications, and the automation of responses to reduce downtimes and improve you know, fault detection and other things that will lead us to better grid operations and more reliability. Another important concept, I think, that is increasingly of priority for policy decisions is the idea of resilience. And that if we have a more modular and a more distributed distribution system, that when we have large harmful events that are of longer duration, that modularity and the interoperability of those interconnected components can reduce the costs of events to the communities where they happen. And finally, if we have interoperability, we avoid you know, replacing technology and replacing devices and replacing systems because we can just you know, pull components out and replace them rather than having to replace entire systems. So I think that there's a good affordability angle there as well. Since I did introduce resilience into the mix, I wanted to just put a pointer in here that resilience and reliability are indeed very different things, and one of the biggest arguments that I think you will face for the benefits of interoperability is resilience. And so I wanted to particularly point out NARUC's April 2019 report on the value of resilience for distributed energy resources. And that the resilience, as opposed to reliability, resilience is really the ability of a system to return to some base state of operation after some large you know, negative event. Part of the challenge in resilience is that when we talk about the system here, we're talking about the community as a system and not just a technology system, right? Not just the electricity distribution system. And that resilience is important to distinguish from reliability because it means larger events of longer duration, and that when we think about resilience, we also focus on post-event recovery, whereas reliability, we tend to think of the traditional SAIDI, how quickly does the system come back after a short duration event. Resilience is very difficult to quantify and value for this reason, because it's a little more amorphous, but it is something worth being precise about and being specific about and being able to say something qualitative about. So I think this NARUC study from April 2019 should be helpful in putting that in the mix.